Okay, so remember that lecture notes are on the website. So if you want to see what we've covered, if you can't keep up with what I'm writing, you can go back and look at those. And then lecture recordings are on the YouTube channel. Okay, and then link on website. So if you want to watch those, or if those are helpful, great. If they're not, you know, you need to figure out what works best for you in terms of your study style in this class. Trying to think. Trying to get, if you want help. So my available hours for extra help: Monday, Wednesday, 1 to 5 p.m. I'm available for appointments. Okay, and you can make those using Navigate, or you can just tell me the day of in class that you need an appointment for whatever time. Okay? Questions? All right. There's also the tutoring center. I don't have a link for that, but you could do Roanoke College tutoring. You'll get that. Yes?
Is the homework on a cheat?
The homework will be on a cheat. And pretty much every other homework will be on a cheat. I don't think I'm going to use the rest of the math modules. My colleagues have indicated they have concerns with some of the later ones. I don't know if it's the next one or the one afterwards, but there are some errors in there they don't like. So we won't use them. Okay, so we're going into chapter 2. We're going to really start focusing at looking at things at the molecular level and the atomic level. We're going to talk about parts of the atom and things, hopefully today. And so I just want to remind you, we have some definitions. Okay, remember that an atom is the smallest particle of an element. And a molecule is the smallest particle of a compound. All right, so in other words, if I was to take, I say I have some aluminum foil up here. So when I say the smallest particle, aluminum is an element. All right, if I go up here to the periodic table, we'll talk about this more today as well. There's aluminum right there. I can take this aluminum, I can divide it in half, and it's still aluminum. I can divide another piece in half, and it's still aluminum. And I can divide it in half, and in half, and in half again, and it's still aluminum. Eventually I'll get to a point where I have to use a laser to divide it up in half, okay? And until I get down to an element, it is still aluminum. Until I get down to an atom, and then the atom is the point where if I divide it again, it stops being aluminum. Okay, does that make sense? All right. And so by being aluminum, I mean it has the properties of aluminum. So once again, I want to emphasize that I want you to be viewing things like a chemist. We view things at the atomic level. We think about, what does this thing look like? Okay? This is a cartoon of a protein. There's other things in there as well. But I'm going to go ahead. Let's do this. I'm going to hide everything. And then I'm going to show everything as spheres. This is how I would look at that. It was a protein. It's got some waters around it and stuff. And apparently they're all close enough that we see them all together like this. Or maybe it's not showing me the waters. But this is how I would view that protein. It is a bunch of atoms stuck together. Each of these atoms is a sphere. Okay? So that's how I would do that. I bet you got a bunch of red spheres over here. Red is, when you see these things, reds are oxygens usually. And so I bet you these are some waters. Okay? This model right here doesn't show me the hydrogens, but I bet you I can get them. Show. let's see. I may not be able to. In which case, I may not be able without commands, and I would need to talk to ChatGPT to remember what the command is. But let's go ahead with show hydrogen and see if it's as easy as that. Nope. All right. So, but so we can look at those. But that's the way I want you to look at this sort of stuff, okay? So I'm not going to be able to bring up a water easily, so I'm not going to, okay? But we've seen some waters before, and I will show you examples again in the future. All right. So when we talk about these atoms, these atom things we see, they come together in whole number ratios in chemical reactions. So if I was to think about this is the reaction that you guys seen pictures of the space shuttle, or you've seen other rockets, right? Well, I'm not actually sure what fuels like the SpaceX rockets, but if you think about the space, you guys have seen pictures of the space shuttle? Okay. One of the main reactions that makes put the space shuttle into orbit was it took hydrogen gas and it combined it with oxygen gas to make water. Okay? And so I'm going to balance this, which we'll talk about in a while, in more detail in a while, but essentially what would happen there is I'd have two hydrogen molecules, so this is a diatomic element molecule, and two of those come together with one oxygen molecule to make two waters. All right, and that releases a ton of energy, and that's why you can actually see that's why that shoots the spaceship or the space shuttle. It did shoot the space shuttle into orbit. And so they're coming together though in whole number ratios. There are four of these with two in terms of the atoms, right? I can multiply that 2 times that 2 to get 4. There are 4 of these and 2 of these to make 4. There's 4 hydrogens over here. Do you see that? And there's going to be 2 times that 2 oxygens over here. I didn't lose any. Okay. That make sense? So if I was to draw this as pictures of molecules, just the way I've got it here, I would have 2 diatomic hydrogen molecules. Let's make those black. I have one, and then I have another. So those are 2 hydrogen atoms stuck together, and I've got 2 of them. Over here I have 1 oxygen molecule. So I've got those 2 atoms stuck together there. All right, and then what that makes is it's going to make 2 water molecules. So these 2 oxygens are going to split apart. And these 2 hydrogen molecules are going to split apart. Each of the hydrogen molecules, the hydrogens are going to split apart, and I'm going to end up with hydrogens, and I'll actually draw them in a different spot. These molecules can rotate. They don't have to be Mickey Mouse shaped. They don't have to give you Mickey Mouse on the side looking through a window. Okay, so that's really, I want you to be thinking about these things split apart, these things split apart, they come back together. That's what a chemical reaction is. Questions? All right, and so what we mean is that when we say they come together in whole number ratios, is we mean those ratios are fixed as well, right? It's always going to be twice as many hydrogen atoms as oxygen atoms coming together to make 2 water atoms there. So I could also write, it wouldn't be the fully reduced form, but it would still also correctly describe the chemical reaction. I can multiply each of these by 2. So 4 hydrogen molecules come together with 2 oxygen molecules, okay, to make 4 water molecules. Does that make sense? Yes.
So on the first one where it's 2 hydrogens with 2 oxygens, with the final product, do we still have 2 oxygens in that?
You do have two oxygens in it. We'll talk more about how these go together, not today, but I'll ask you to take my word for it. Imagine the molecule itself. That's a great question. Imagine the molecule itself has parentheses around it, like in math. So this little 2 means there's 2 hydrogens.
Yeah.
And then this is 2 times everything inside the parentheses or the molecule. We'll talk more about that. We're not going to do a lot of it today because we're not going to be balancing equations or anything today. But I do want you to be thinking about this. I want you to see these whole number ratios, right? And partially because I'm going to introduce a concept I've already talked about or already mentioned in this lecture, which is that matter cannot be created or destroyed in chemical reactions. Okay, that's a law we're going to use in here. Okay, that is the law of conservation of matter. And another way of phrasing it is that atoms are not created or destroyed. All right, you have the same number in the reactants. The reactants is this side and the product is this side. Let me go ahead and write that right now. We'll emphasize it more later, but it's always good to repeat these things. So these are the reactants, and these are the products. Okay, when I draw that arrow. But so I'm going to go ahead and rephrase this right here. I'm going to say atoms are not created or destroyed in chemical reactions. And we'll just say the atoms rearrange. They change which atoms are bonded to which changes. Which is not a very technical way of saying it. But so in other words, what we had is we had hydrogens bound to hydrogens, oxygens bound to oxygens, and now we have hydrogens bound to oxygens. That's a chemical reaction. And it's a chemical change. This is what a chemical change looks like at the molecular level. A physical change, you would start with waters and you'd end with waters, right? They might be gas in the air. They might be ice in your drink instead of liquid water. But it would still be, all the atoms would still be bound to the same atoms in terms of the molecules or elements or elemental molecules. Questions? Okay. One thing I want to point out here is your book talks a lot about the history of things, especially in this chapter. And those stories are really important, and I remember being taught them myself. I'm not going to spend much time on them. I may actually assign them as one of these achieve assignments in terms of the reading if I feel like I'm happy with it. And it would be like the assignment you guys just did. So it would be one of those everybody can get full credit sort of assignments. So I don't plan to emphasize those very much, and I'm not going to emphasize those in class because I want to get through the material we need to get through today. Okay, but we are hitting the important points. So when I talk about this law of conservation of matter, and when we talk about this rearrangement, Dalton is the one who came up with atomic theory for the first time, and everything he said was right there. Okay, I'm not going to talk about that. I'm not going to emphasize that. But people actually came up with these rules that are in our textbooks that we just take for granted now, and they did it doing experiments. Okay? And so part of the history is knowing the experiments. How do we know what we know? Because it hasn't just been made up. Okay. So one other thing I think we need to emphasize here, atoms are really tiny. You probably know that already, right? You can't see them with the type of microscope you'd use in biology. And I'm going to call that a light microscope. Okay, a light microscope is the type of microscope that you would use in biology, and it uses regular light. It uses the light that we use to see things with our eyes, and it just can't. It can go down to about the size of a bacterium, and it can't go smaller than that. And bacteria have thousands and thousands, and well, probably millions, let's say, more than millions of atoms in them. Okay. You can see them with some sorts of microscopes, and there's this very cute picture of IBM spelled with atoms in your book, okay, where IBM did that, and that's a scanning tunneling microscope. We actually have a tunneling electron microscope downstairs. I don't know whether it can go all the way down to atoms or not, but it can go really small. Okay. Questions? Okay, let's talk about the size of an atom real quick. Atoms are roughly 1 angstrom in size. Okay, and when we think about an angstrom, what is an angstrom? Okay, well, what I want you to remember is really not what is an angstrom, but an atom's about an angstrom in size, right? And as you get more of a general feel for scale, you might get that. So 1 angstrom, or let's say, yeah, let's do it like this. I'll do it both ways, and I'll ask you which one is better. They both might be just non-intuitive. So 1 angstrom and that's how you do an angstrom actually, but I don't know how to do it quickly with that. So 1 angstrom is equal to 0.000000000 meters. Okay? How could I have made my life easier there? Scientific notation, right? I could have said it's 1 times 10 to the negative 10th meters, right? That was much more pleasant, at least for me. Okay? Or you could say that there are 1 0 0 0 0 0 0 0 0 0 0. There we go. Angstroms in 1 meter, or there are 1 times 10 to the 10th angstroms in 1 meter. Just to give you a feel for it. I don't know that that helps at all. Is either of those better for you? Which one? Which one do you like better? Do you like lots of angstroms in a meter, or a very small fraction of angstroms in a meter?
Lots of angstroms in a meter.
Lots of angstroms in a meter? What was that? Fractions. Let's see a vote. See if there's a huge difference. I'll maybe express differently in class. Lots of angstroms in a meter. Fractions of angstroms in a meter. Oh, it's about even. All right, I'll just mix it up, but I'm not going to probably do both all the time. But if you ever want me to express it a different way or you're confused, let me know. For contrast, let's go ahead and I'm going to run the number out again. A bacteria, which you've never seen directly either, is about that many meters in length, okay, compared to that angstrom. Questions in terms of size here? Super tiny. So we're visualizing these models, and in science we use models to describe things, okay? We're not necessarily describing them exactly how they look in reality, but what I've shown you with the balls, that's a great model for us to use for now. And as you go on in science, if you go on in science, what's going to happen is the models are going to get more and more refined. So they're going to get more and more correct, right? We're going to use approximate models and they'll get more correct, then they'll get more correct. And what I mean by more correct is they do a better job of fully explaining the natural world, okay? All right, so then let's talk about the periodic table. The periodic table is super important in chemistry, and so we have it over here. And this one has all the, this is old, this has all the elements we'll ever care about in this class on it, and more, okay? And so what's fun about this, or what's great about the periodic table is that it tells us a lot about the chemistry. So this was originally arranged by Mendeleev. He was a Russian chemist, probably physicist, probably hadn't invented chemistry yet. He arranged the elements by their reactivity. So elements that are in the same column have the same reactivity. Or similar reactivities, I should say. It's arranged by columns and rows. The most important parts of this are the columns. So elements in the same column have similar reactivity. So what do I mean by that? If we take this column right here, let's take this column, oxygen, sulfur, selenium, tellurium. I'll just do the first three. But if I react, so as an example, if I take hydrogen gas and I react it with, so this would be a molecule of hydrogen, and I react it with sulfur, what I'm going to get is I'm going to get H2S. I'm going to get 2 hydrogens per sulfur. If I take a hydrogen and I react it with an oxygen, okay, I'm going to do this half oxygen, so it's only 1 oxygen. Is that half confusing? Let's not balance these equations. I'm not going to worry about that yet. It'll be less confusing. I'm going to get hydrogen. I'm going to get water, essentially, but 2 hydrogens. If I do the same thing with selenium, I'm going to get 2 hydrogens will stick to the selenium. Okay, does that make sense? So it doesn't have to be hydrogen, but hydrogen's easy, right? If I take hydrogen and I react it with phosphorus, I get 3. If I take hydrogen and I react it with nitrogen, I get 3. That's what I mean by same reactivity. Okay, it doesn't have to be hydrogen, but here I'm using that as an example. These, same column. And these, same column. Okay? Questions? Yes?
So can you explain why there's a 3rd hydrogen after adding the other element?
How there's 3 here?
Yep.
So I'm not balancing these equations. I'm violating our law of conservation of mass here. I could balance them so they all worked out. If I was to do that, I'd have to do, well, let's see. If I do 6 and 2, that would do it. So I'd have to do, I'd have to do 3 and 2 and 2 to make that work. Does that answer your question? But I don't really want to emphasize this balancing equations, yes. Do you agree that now that I have So I added 2 to 1, and I didn't make 3.
Yeah.
It would have to be 3 hydrogen molecules reacting with 2. Nitrogen isn't even nitrogen's diatomic, so this would become more complicated still. But two nitrogens to make this. If I was fixing it so it actually followed the law of conservation. But these are the molecules you'll end up with. And we will go over that in great detail. The main point later on in the course. The main point here is that the molecules that get made from this reaction, the molecules you get made here, that phosphorus, you see phosphorus and nitrogen are in the same column there, 15, right? They would make 3, they would make these molecules. Oxygen, sulfur, and selenium are going to make these molecules, so 2 hydrogens per. Same similar reactivity there, and that's why they're arranged in the columns they're arranged in. Okay? We also have rows on the periodic table. So let's say, as you move down rows, elements have more elements that get heavier. Let's just leave it like that for now, okay? Super oversimplification, but it's not super important at the moment. We're about to talk about electrons, parts of the atom. And so we talk about protons and electrons and neutrons. Well, let's just talk about protons. As you move down the periodic table, you get more protons. And in fact, the way it works is you get more protons, you just move it just like reading. So 1 proton, 2 protons, just look at this red number, 3, 4, 5, 6, 7, 8, 9, 10 protons, etc. Just keep scrolling down. But in terms of reactivity here, there will be some trends we'll talk about, but things aren't grouped in this direction, if that makes sense. They are grouped with 5 columns. Yes?
What's the element covered by the sticky note?
The element covered by the sticky note is hydrogen. Okay, you see how we have hydrogen on both sides? Hydrogen sometimes acts like this, and it sometimes acts like it's one of these, but not in this class. Okay, we're not going to go over that. It's important when you take organic chemistry, you will see hydrogen. In organic chemistry, it's a sophomore level class. You will see hydrogen sometimes act like this. Other questions? That was a great question. Okay. Let's see, where are we on time? All right, so there are pieces to the periodic table here. We've got it over there. I'm going to go ahead and draw my own periodic table. So it sort of looks like that, right? Okay. We have other parts that I'm going to talk about because the names get used, and I may use them as well. Okay. So as chemists, we talk about a couple different parts. We'll break the periodic table into groups, and we will talk about, just imagine a thing that goes down there on the periodic table, and you don't need to know these exactly, and I'm not even going to, I might vaguely test you on these terms, but mostly it's just you need to, if somebody's talking about metals, they mean that part of the periodic table. So all of this, and you can actually see up here, there's a line. Do you see this line? Right? These are all metals. Everything over there is metals. These are all metals. These are all metals when we talk about it. All right. If you like watching, cosmology. When I say cosmology, I mean deep space. People talking, astronomers talking about things. They consider everything that's not hydrogen and helium a metal. So it's all the different definitions. But you probably don't watch those. Don't worry about it. But it's a fun. It's not the chemistry. The chemistry definition is everything. This side is a metal. Okay? And it has the properties you would expect for metals, right? This is aluminum. What kind of properties does this have? I can bend it, right? But
It's soft.
it's soft. You can melt it, right? Okay. What else? Shiny, right? Okay, all of these things. If you were to make a solid piece of it, like a foil, it would do that. Okay, except mercury is going to be a liquid. But mercury, if you see mercury, it is shiny. Okay, so those are all metals. If I was to take this again and kind of do which isn't on our periodic table up there, all right, these would be our nonmetals. Over here. And so our nonmetals are going to be, if I take this little line here, if I was to draw another line, just one off of it, like that, it's not on the periodic table. Let's take everything just one to the left of this line on this periodic table. These are nonmetals. So starting with carbon, phosphorus, selenium, iodine, radon. Radon? Radon. No, radon. Questions? Okay, and so we'll talk about metals and nonmetals, and we might occasionally talk about metalloids. Two L's. Okay, and metals are elements that have properties that are a little bit like metals and a little bit like nonmetals. They're sort of between them, and they're kind of important. I mean, lots of things are important for semiconductors, but they're important for semiconductors because they kind of act as so boron, silicon, arsenic, palladium. They kind of act like both. They help run our computers, our phones, everything else. So I just want you to be aware of those terms, more so metals and nonmetals. There's also, I'm going to go ahead and draw my periodic table again here because I don't want to make a big messy picture. Another term that we will use, and I want you to, when we use that term, I want you to know I want you to immediately kind of know where we're talking about on the periodic table. Okay, and that's transition elements. And everything, these are transition elements. So if I go over to the periodic table here, transition elements are everything, you got this kind of tower here, everything from here to where we start going up again. That's the tower there. All right. And then these are lanthanides and actinides, and we have I'm trying to remember what group to call them. We're not going to worry about what to call them. They don't get referred to that much, if that makes sense. Okay. Not that we don't have important things down here, we might not talk about them. We've got uranium. You've heard about uranium, probably. You've probably heard of plutonium. They're down here. But in terms of thinking about chemical reactions, we're not going to talk about them. I'm not sure whether we actually cover nuclear chemistry in this class or the next one, or at all. In this, it's sort of a different thing. It is probably in your textbook somewhere, and we may or may not cover it. We'll see. Okay. Questions? All right. So I want to talk then about charges, right? Okay, so I don't know if I said this first lecture to you. I always say it to biochemistry students because I've had enough chemistry to appreciate it. But you could explain, so I've taken a lot of chemistry. You know, I did chemistry in high school. I was a chemistry major and a biology major in college. I went to grad school. I did chemistry there. I've taught chemistry ever since, right? So I've probably been chemistry 40 years? At least 30 years, okay? 30, 40 years of chemistry here. And what I can tell you is you can explain most of chemistry using charges. And so that's the attraction or charges attracting or repelling each other. And they don't have to be full charges. And here we will talk about full charges. We'll also maybe talk about partial charges. But there are full charges, there are partial charges. In the research I do, which is computational, charges are super important. But you can imagine, so if we think about your car battery, we use color. I'm going to try to use the colors of the car battery, okay? The red is the positive. The negative is going to be black, okay? And so here we have a positive charge and a negative charge, and they're going to attract each other. So opposite charges attract. Okay, and then like charges repel. It's not. All right, so we could have two positives or we could have two negatives. Does that make sense? Maybe heard that before? It's sort of like when you take a North Pole and a North Pole of a magnet and stick them together. You've probably done that, felt them repel. Same sort of thing here. And then if you get the poles opposite, the North Pole or South Pole, then they will attract. And when we draw charges, I just drew these as single charges. You could also have multiple charges, so you could have a 2 plus. Okay, so 2 whole full charges. Oh, actually, I should do that in red, but I didn't. Here, I'll fix it. Okay, you could have a 3 minus. And those would attract as well. They wouldn't have to match or at all. Okay. If these attracted each other and stuck together, there'd still be a negative charge overall, and we'd be looking for another positive charge someplace to neutralize it. All right, we have an equation that we can use to describe the strength of that attraction. So the strength of attraction using Coulomb's law. And essentially what we're talking about here is we're describing, you know, electromagnetism is kind of what we're getting into here. I don't know if you've heard about that. Does anybody watch any of these physics videos? I find them fun. A lot of them are over my head, but okay. Anybody ever heard of dark matter? Okay. So when you think about electromagnetism, the deal with dark matter is this matter they use to explain how things move around because they can't see all the matter in the universe, right? They can only see, it's about 15% of the matter or something is what you can see, and the rest of it is the stuff that you can't see or detect in any way. And the deal with dark matter is it doesn't interact with charges at all, or magnets at all. Okay. And so everything we see is electromagnetism. Everything you interact with, you see it with your eyes. When you touch this table, there are electrons in your fingers and electrons in the table. And I can't push through this because my electrons are essentially repelling. There's an electron shield on both of those. Okay. So everything Everything you see, touch, taste, everything has to do with electricity and magnetism. And charges would be the electricity part, yes.
So like when you randomly get like shocks when you touch something
Yes.
by accident,
That's charges. That's actually, when you touch something and you get a shock, what's happened is you've developed a slight excess of a particular charge on your body, like by shuffling your feet on the carpet. You end up with, I don't know which way it is. I'm going to say it's negative, but I might not be right there. So let's not take that at granted. But you get a slight excess charge on you. You touch something where it has either a slight excess of the other charge, or you just touch something and ground yourself. The charge comes out of you, and you get a little shock when you do that. And you're mostly going to feel it in your finger where you're touched, right? Because that's where it gets most concentrated as it goes out. Does that make sense? So yes, absolutely, that is charges. All right, so we can explain this using an equation, which is Coulomb's law. And so that equation says that the force of attraction is equal to some constant times the charge of one of our atoms, we'll say, okay, or molecules. We'll work with atoms here. The charge of one of our atoms times the charge of our other atom. Okay, and I want to start using the term ion, so I'm going to define it. Ions are charged atoms or molecules. So if I have a charged atom or a charged molecule, I will call it an ion. Let me go ahead and label these things on the equation for what they are. So this is the force of attraction. Okay, or repulsion here. All right. It's the force of attraction or repulsion. And then this is a constant. And it's essentially a constant to make things work. Okay. This is going to be the, what we're going to be using is like if it's in a vacuum, we're going to be using a constant. But it's a constant. If we were in water, we'd use a different constant. By the way, this equation is super important with my research. This R is the distance between the ions. Okay, and then Q1 and Q2 is the charge, the whole number charge on the atoms. So the whole number charges of the ions. Okay, so that's where we are with this. So this constant, I'm going to come back and add something to this equation, but I want to show you how I would do it. I'm pretty sure I know what the units are for that unit there, for this distance. Okay, I think they're meters, but I'm going to look at my notes, which I haven't done yet. I'm going to look at the constant, and that's going to tell me. Okay, so the constant we're going to use here, and I will give you all constants in this class. Okay, the constant is, so KE here is going to be equal to 9.0, it had more digits in your book, times 10 to the 9th Newton, which is a force, meters squared over coulombs squared. Okay? We've done our dimensional analysis. Is this on the top or on the bottom? It's on the top. Okay, so I've got meters squared on the top. In the end, it's called Coulomb's law. I'm going to want to get coulombs out. Or I'm going to actually want to get some force. I'm going to want to get newtons out. What I'm going to want to do is I want to get rid of this meters, right? So what do the units here have to be? Meters, right. If this is meters, this has meters square in it, and this is meters squared, then the meters on the top cancels, meters squared on the top cancel with the meters on the bottom. Does that make sense? Okay, so what this is the distance in between in meters. Okay, and then it gets squared. Questions on how I did that? Okay, we have 3 minutes here. I could work one of these. All right, so let's say to use this equation, if I wanted to figure out, so I could say, what is the force?
And that's it.
I know, I'm trying.
Sorry.
I appreciate it. What is the force? If something's not displaying on the screen, you gotta let me know as well. I appreciate that. What is the force of, well, I'm not gonna tell you what it is. What is the force between a 2 plus magnesium ion and a 1 minus chloride ion at a distance of, let's go 5 angstroms. Okay. So I'm not gonna have you work this one. I just want to set it up real quick, and I may not even put the answers into my calculator based on our time. I will finish it and then put it in the notes, in the post-it notes, and then you might have practice problems on this. But this is essentially putting things into the equation. But 5 angstroms, I'm just gonna do this in my head for time here. But 5 angstroms is gonna be 5 times 10 to the negative 10th meters, right? Based on our conversion factor above. We could do that conversion. And so now I would just put this all into the equation. So this was absolute value, okay? It was absolute value. That's what that sign meant. I didn't say that up there. I'll add that. But it's absolute value. It's going to be 2 plus, right, times 1 minus. If I was using my equation up above, I'm just putting them in. R squared is going to be 5 times 10 to the negative 10th meters squared, all right, times 9.0 times 10 to the 9th Newton times meters squared over coulombs squared is equal to what my force is going to be here. And I see I'm out of time, so what I will do is when I get back to my office, I will work this the rest of the way and post it. So you'll just be able to see what happens after I put it through my calculator. And we'll either do more of these do another one of these on Monday, or maybe I'll have you do some practice ones. Okay? You guys have a great weekend.